Any questions? All right, we last left off solving AC circuits. And if I can see someone's notes from the last setup that we did. So that was an RLC.
Yeah.
Oh, I didn't get it. Oh, is that from the video? No. That was in the class. Must have been in a Warrior Haze kind of thing. All right, that sort of sets up a foundation there. I'm going to give you I'm going to jump to a different problem. We're going to solve it with phasors, we're going to solve it with the imaginary stuff, and I guess the complex number look. AC power supply, of course. Resistor, inductor, capacitor. VRMS is 120 volts and frequency of 60 hertz. Because apparently when I was writing this problem up, I had no imagination. And the question is, each of these, there's going to be a current coming out of the power supply, a current going across each of the components, and then each component has a voltage. So there's basically 4 phasors that we would need to deal with here. So if we draw up the phasor diagram, so what do we have in common? That's going to get annoying. That silence it. When we're starting a phasor diagram, we should start with something that is common. Is there anything common to all 4 components?
Current.
So current would come, if current's common to all 4, then that implies that there's no junction in between any 2 components. So considering we have a junction here and here, current is not going to be common to all of them. Voltage, it's either current or voltage. Is the voltage across any component going to be the same? No. I mean, even though the voltage across here and here would be the same, and the voltage across both of them is the same, but not across that and that. So when starting the phasor diagram, we need to pick a phasor that is common to the most things. And we have 2 choices there, one of which will take us into a very difficult situation, and one of them takes us into a much nicer situation. How do you know up front? Well, for me, I started with the other one, found out that it was much more difficult, and then went to the easier one, or the one that turned out to be easier. So what's going to be common to 2 things? be simpler to think of it as a DC power supply. All right, so I've got power supply, resistor, inductor, capacitor. And I've got, each has a voltage and each has a current. I guess as far as formulas go. Voltage and current. Which two components would have what a voltage in common?
The power supply and the capacitor.
All right, so I've got power supply and capacitor. Which two components would have the current in common?
R and L.
Yeah, resistor and inductor. So those are the two choices that we have to start out our phasor diagram, and I'm going to start with the voltage. So that would be the voltage of the power supply, which we usually label as epsilon sub naught, and voltage of the capacitor. All right, from that I know the current of the capacitor. In which quadrant is the current of the capacitor?
The second one.
Oh, sorry, I thought you were pointing to the fourth one.
I was thinking.
All right, but you're saying second?
Yeah.
Yeah, because for a capacitor, the current leads the
Yeah.
EMF. So it's supposed to be a right angle. Yeah, closer. I for the capacitor. The trouble is, we get to this point and I'm not really quite sure where the voltage of the resistor and inductor are. I know that whatever these voltages are, they have to add up to this. And I know that the current coming out of the power supply must add up to IC plus whatever the current is flowing across here. So this is a much more difficult way of approaching it. And the main reason I went down this path is just to show that when you start doing a phasor diagram, you might end up with the more difficult choice to start with. It's okay. That just means you stop and you try something else. So we're going to do the current one. And so I know that the current out of across the resistor is the current across the inductor, which I'll label as IRL. All right, where's the voltage phasor for the resistor?
The in phase.
Yep. Sketch that one down. Where's the voltage phasor for the inductor?
The fourth quadrant.
Eli, inductor L, E for EMF.
You said the voltage?
The voltage. It's not the fourth one.
Second.
Yeah. Right. Never do it at an angle. It's tough enough straight ahead. That's DL. So for the inductor, the EMF leads. Again, these are areas that are all rotating counterclockwise. It really would have been convenient if clocks had been designed to go the other direction. All right, so I know that the sum of those voltages has to be the voltage across the power supply or the capacitor. So I'm going to add them like vectors. And so I have this epsilon sub naught or which is also VC. I now know the voltage of the capacitor, or where that phasor is, so where is the current of the capacitor?
Second quadrant again?
It is. So we do another 90-degree angle, it's just gonna be just above the horizontal. And so that is current of the capacitor. And our last bit is the current coming out of the power supply. I know that power supply splits between the RL path and the C path. And so the sum of the current across the capacitor and across RL has to be the sum of the power supply. And so I would add them again like vectors and say, so this should be like that and like that. And that's I power supply. Just because I drew it this way, I've got VL and VR, sorry, I have VL and IPS sort of overlapping. It's going to turn out that IPS is just slightly to the left or slightly leading VL. So the way I've drawn it is not a great reflection of it, but it's the best you can do when you don't know numbers yet. All right, we have our phasor diagram, now we need some numbers. A little bit of law of cosines coming up, just to get you pumped and excited for it. Law of sines, maybe, depends on your mood. All right, so what do I know? I added two things together, and I added VL and VR together to get VC. Pythagorean theorem. So VL squared plus VR squared is equal to epsilon sub naught squared. Again, these labels I have, these are the magnitudes. This is the amplitude of these. The instantaneous value is the projection onto the horizontal axis. What is epsilon sub naught anyway? Numerically, I'm looking for a numerical number answer, or how you would figure it out.
Would be the RMS times the square root of 2.
Indeed. So based on our RMS value, I know that epsilon sub naught is equal to 120 times the square root of 2, which is 169.706. Going off of memory. Okay. What's omega, since we're here? What's the angular frequency?
60 times 2 pi.
Yep, that's supposed to be an omega there. Which is 369.99.
3. I got 376.99.
376, oh, okay, 376.999. Units?
Readings per second.
Yep. All right. So I have this bit of information here. So I know epsilon sub naught. I don't know VL or VR. I do know one thing about them though. I know VL and VR both have the same current. Therefore, I know that VL, I'm going to hold off on substituting into there for right now. I know VL is equal to my IRL, whatever that current is, times X times my inductive reactance. And I know VR is equal to IRL times my resistance. So based on this, I know that IRL is equal to VL over XL. It's also equal to VR over R. So I can come up with a relationship between VR and VL based on this, because I have two unknowns here. I have another equation here with two unknowns. It's solvable. Well, we can solve for XL, we haven't done it yet. So from this, VR is equal to R over XL VL. R is, in theory, given. I didn't actually give it to you. Why don't I give numbers to you? So my resistance is 15 ohms. My inductance is 45 millihenries. And my capacitance is 200 microfarads. So R 15. What is XML? What is the formula?
VL over I.
Looking for a more basic formula.
Isn't it like 1 over the angular frequency times the capacitance?
That would be X sub C. So while we're here, why don't we go ahead and do that one? That's 1 over omega C, which is 1 over 376.99 times 2 times 10 to the negative 4th. So what is our capacitive reactance?
.0754.
0.0754. Did you take the reciprocal?
Yes, sorry. 13.263.
13.263
Yes.
units.
Cross.
And I'm definitely not saying I wouldn't do it, but it always surprises me that whenever I ask for units, the number of people who look at their calculator, that they, it's a common thing. Anyway, X sub L. What's the formula?
Omega L.
Omega L. Yeah, there we go. So 376.99 times 0.045.
16.965.
Units.
Ohms.
Yeah. All right. All right, so now we're back over here. We have a pin somewhere. There we go. So R is 15. X sub L is 16.965 times VL. What is that?
0.88419.
88419 VL. All right, if we plug that into our equation up here, we have VL squared plus 0.88419 VL, that whole thing squared, is equal to our epsilon sub naught, which is 169.706 squared. I have, in this part, I have VL squared common, so I have 1 plus 0.88419 squared times VL squared is equal to that. And so VL is gonna be 169.706 divided by the square root of 1 plus 0.88419 squared. And we end up with
Is that 169.706 or 16.9?
no, 169. It's epsilon's not.
Oh.
One 27.136 volts.
1364.
36 volts.
127.364.
136 volts.
So 127.1364.
Volt.
No, volts. I was saying volts. so-
Oh, volt. Okay.
No 4.
No 4.
It's a 0.
Okay. There we go. Sorry, your deep southern accent. Couldn't tell. All right, so we know what VL is. Now we can figure out what VR is because we have a relationship right here. So VR is equal to 0.88419 times that 127.1360.